Uh, Thanks for those who came in person today. Appreciate you showing up to support our speaker today. Dr. Miriam Diamond is a professor at the University of Toronto in the Department of Earth Sciences. She's an international expert in chemical contaminants from sources to management. And I saw her give a plenary at the International Society of Exposure Scientists meeting in 2023 and thought that her research, which spans from identification of chemicals, their sources, their transport, human exposure, and ultimately policy recommendations touches a lot of the aspects of our diverse department. So her group uses broad methodologies to develop defensible strategies to reduce chemical contaminants like PAHs, microplastics, flame retardants, pesticides, and many others in the environment. She is a former associate editor of the journal Environmental Science and Technology and was named the Canadian Environmental Scientist of the Year in 2007 by the Canadian Geographical Society. So join me in welcoming Dr. Diamond.
So Kirsten, thank you very much for that warm welcome. And thanks to you for coming, and thanks to everybody online who is here. Yeah, chemicals of concern, which I'm sure you know all about, and our inevitability of exposure, and hopefully solutions. So I want to share with you, I'm not very good at standing still. So I think I wanted to be a stand-up comedian in my life. So I'm going to take, for those of you online, you're not going to see me because I'm going to be moving around a little bit. So I spent most of my career in the ivory tower. And I was drawn to the ivory tower because I want to do good. I want to help the world. I want to save the world. And while I've been in my ivory tower, the traffic congestion in Toronto is now 12 lanes of highway as I've been in my ivory tower. So clearly I have not been all that successful at changing society as a whole. But I've certainly wanted to, and I've done my best to make a dent in that. So to tell you a little bit about what I do, I stay and I work in my ivory tower, but do what I hope is research towards the public good and that is animated towards the public good. So I do work on fading exposure, as I'm going to explain, and as Kirsten mentioned. But I'm also commissioner. Who ever heard of that? But anyways, the Earth, there's an Earth Commission out there. It's run by Future Earth. The goal of the Earth Commission is to come up with Earth system boundaries that are both safe for biophysical continuance of the world and just because of equity. And then strategies to move those boundaries towards actors who can work on bringing us within those boundaries. So I do this work with Johan Brookstrom and a group of international scientists. It's very interesting and also hopefully impactful because the boundaries have planetary boundaries and Earth system boundaries are a good communication tool as well as providing updates on science. But the other thing I do is hopefully work towards adoption of our work. And that is right now under the auspices of the United Nations Environment Assembly, Resolution 5.8, is the establishment of a science policy panel on chemicals, waste, and pollution prevention. So what UNEP has noted is that we're facing the triple planetary boundary, and that's climate change, loss of biodiversity, and chemical pollution. This panel will hopefully take its place beside the IPCC, which is for climate change, IPBES, which is for biodiversity, and a new panel then for chemical pollution. And for those of you who, no, I'm going to come back to that. And then the last thing I do is with the Global Environment Facility. How many of you have heard of Global Environment Facility? Oh, thank you.
I worked at the World Bank, so.
So you know that it's a World Bank administered fund from donor countries with projects intended to help with the implementation of, there's so many words, multilateral environmental agreements. That's the Stockholm Convention and the Desertification Convention and a number of other conventions. So it's money that goes from donor countries to low-income countries to help with the actual project implementation. And this has really changed my thinking a lot because it's a huge difference or distance from the ivory tower to actual implementation in low-income countries. So here's my argument today, and now I'm a little bit embarrassed because Kirsten, this is a redux, but don't worry, I do have some new slides. So the inevitability of exposure, our inability to sufficiently reduce exposures to protect populations, and why. I'm going to go through these 4 different points and then end up on solutions. And by the way, how much time do I have?
We usually end at 1, so.
But does that include questions and answers? Yeah, that's okay. Is it awful when speakers just go on and on and on? So, okay, so you've probably seen this graph. I mean, like, why do I get up in the morning and do what I have to do? Because I'm convinced that early life exposures and the important work that Jiong is doing on, did I pronounce your name correctly? I'm so sorry. Jihei is doing, I beg your pardon. The important work that Jihei is doing. If we have time on this axis and the number of people affected on the y-axis, then we see that there, for example, if you take lead, that there's neurotoxicity expressed in adults, and then there have been acute poisoning incidences. If the chemical is very persistent, if there's widespread exposure, then it moves into subclinical effects, usually on children, because as you know, children are more vulnerable, and then into a silent pandemic. So I'm very motivated by this paradigm, and very disturbingly, I'm sure you've seen these results about increasing cancer rates among younger people that are attributable to increased body mass, attributable to more sedentary lifestyle and chemical exposures. So that's what motivates me, and here are 3 examples. The last one will come about the rampant use of pesticides, including highly hazardous pesticides. I was just recently in Costa Rica and have looked at, for example, paraquat, which is a highly hazardous pesticide, which we don't use in high-income countries because we've passed legislation against it. But some pesticide companies have been highly effective at ensuring that paraquat is still used in low-income countries, which is a failure of global governance. And that's something I wish we could do more on, for example, through the JEF. So highly hazardous pesticides, which causes acute poisoning as well as chronic outcomes. And then, of course, we know about lead exposure that continues. Did you know that the Minamata Convention for Mercury was supposed to include other metals like lead? Which did not pass the muster in terms of when the convention was set up in negotiations. And you know that lead is still not globally controlled. And then the last one, which is the enfant terrible, or the terrible infant, right, the PFAS. So this is data from the European Economic Area that shows very widespread exposures, leading to an estimated 12,000 deaths. And moderate exposure. Can you see the bottom of the slide? Oh, fine. Okay, so I don't actually, okay. So moderate exposures to 3% of the population, leading to low birth weight, infection, and hypertension. So there's a very sizable cost of inaction. And as we go through these turbulent geopolitical times right now, which has been at the forefront, obviously, for all of us, we have to keep hammering this home. The cost of inaction. It is so economically important that we act, and we're not even acting in a precautionary way at this point. Anyways, we just have to keep considering the cost of inaction. So now I want to take you through the arguments, the hypothesis of the inevitability of exposure, our inability to sufficiently reduce exposures in vulnerable populations. Okay, so I know that some of you are in engineering and some of you are in health. So the inevitability of exposure is all about thermodynamics. It's just inevitable, and it's all about fugacity. It's also about chemical production and exposure, and that we're not all equal. So, fugacity. Has anybody heard? I knew, oh, Kate said, I'm sorry, I don't know your name, but I feel very kindred spirits. Good. Okay, that's great. So, if you don't know about fugacity, what you do know, and I don't see anybody with a nice warm cup of coffee or something. But if you did have a warm cup of coffee, you would instantly know that the heat is moving from high temperature to low temperature, right? Yeah, I mean, you just know that. And the equilibrium criterion, which tells you which direction the heat is flowing, is temperature. So you immediately know that heat goes from high to low temperature. It just is. Well, fugacity is the same thing, but for chemicals with a measurable vapor pressure. So if you stuff a chemical into something, for example, just looking at your chairs. So you've got padded chairs, is it vinyl? Is vinyl and foam?
No foam.
No foam, just vinyl? They're not padded?
No, it's kind of like a.
Yeah, okay. So very likely, the polymer that's making up the seat, it probably is PVC, because it's the cheapest. And PVC is a very rigid polymer, so you have to put in a plasticizer. The plasticizer is not chemically bonded to the polymer. So it's got a high fugacity. When you stuff a chemical into something, any plastic additive, any flame retardant, it's stuffed into the polymer, not chemically bonded. It inevitably has to go from high fugacity to low fugacity. So it's going from the material to which it's been stuffed into whatever is the lower fugacity. And that's going to be the air around us, because there is air exchange. And that's going to be us, because we have a finite metabolic lifetime of the chemical in us. We excrete it or eliminate it somehow. So it's inevitably going from high to low fugacity. So that's illustrated here. Nope, that's my former supervisor, Don Mackay, who was a chemical engineer and talked about and sort of brought fugacity and this understanding into the scientific realm. Okay, this is a really old picture of me because I had more brown hair. And it's also an old picture because it's a new TV. Like it was 2008 and it was a new TV. And finally, as a faculty member, after having been promoted, I could buy a new couch. It was so exciting. So the TV and the couch, and I know this because we sampled my living room, both had flame retardants stuffed into them, and they happen to be polybrominated diphenyl ethers. So high fugacity, and of course this is contrived, but because these are nonpolar, because those flame retardants are nonpolar, they're going to migrate, they're going to seek the medium that has the lowest fugacity. And for that, it's going to be something with a very high fat content. So it's going to go into the butter. But inevitably, it goes into me, and that's going to be through inhalation and dermal exposure. So this is, how many of you have seen this study? Oh, good. So this is just like the most both crazy and ridiculous study at the same time. And do you know who these people are? Glenn Morrison and Charlie Weshner. So what they did in Denmark is that they sealed off this office space and they pumped in some phthalates. And the experiment was they're going to breathe clean air and then look at dermal absorption. So you're going from high fugacity now in the air to a lower fugacity on your skin. So, and then they peed into a bottle at different time periods, and lo and behold, both, this is, clean air, breathing clean air. And, oh my God, I'm not doing this fast enough. The open ones are clean air, the closed one is just dermal. So, as expected, from the air, these phthalates are absorbing onto the skin, which has a lower fugacity. And then ultimately going through the body, where they take it in and then they pee it out over time. Because these phthalates have a short metabolic lifespan. Okay, so then. This is so back of the envelope. But I find it pretty interesting. So Bill Nazaroff and some others did this back of the envelope calculation on an intake, production to intake ratio. Expressed here along the x-axis. So it's in parts per million, right? So this is 1,000, but it's parts per million. So what they found, and here are a bunch of phthalates. Oh, that's BPA, phthalates. So what they found is, interestingly, for the phthalates, about 0.1% of production in the US was showing up in the urine of the general population measured through NHANES. So very back of the envelope calculation, but I find it quite compelling because NHANES is supposed to be nationally representative. I find it quite interesting, and I do see the thermodynamics behind it. You produce it, it's going to get into you inevitably, but for BPA, it's a very resilient, it's a very strong polymer. So less of it gets into individuals, and then methylparaben, which is used as an antimicrobial, right, in personal care products, anywhere from a tenth to almost 1-to-1 of production ends up because it's being applied directly. So then other colleagues, Lee et al. Lee et al. Did a much more sophisticated modeling approach, going all the way from production and life cycle assessment and production and fate and transport and food and blah, blah, blah. And lo and behold, what they came up with is 0.1% of production ends up in people. These are a whole bunch of pesticides. These are industrial solvents that have a lower ratio. And the higher ratio here, personal care products. Okay, but as you know, we're not all equal, and you do so much work on that in your institution. So we did a study in low socioeconomic housing. It's social housing, so it's subsidized housing. These are what the units looked like. And we were really astonished and dismayed to find that for every chemical we looked at phthalates and we looked at some flame retardants. Every chemical was 2 to 18 times higher in the low income housing than higher income housing using exactly the same sampling methods. So these are a bunch of phthalates. And of course, the reason why we're concerned about that, and again, many of you have looked into this, but we were looking at the relationship between the concentration of phthalates in dust versus the probability of developing childhood asthma in a large cohort. So I think this is about 1,000 kids. And we found this very strong relationship with diethyl hexyl phthalate, which is very high production volume phthalate. Let me tell you what's different about our study though. We vacuumed the kids' mattresses. The other studies for which there's more ambiguous results look at the most used room. But we vacuumed the kids' mattresses and found that the levels were higher in the kids' bedroom and mattresses than in the most used room. So that led us, I think this is the next one, that we're just, I just resubmitted this, hopefully it'll be published. We looked at kids' mattresses in Canada. We initially purchased 8, because we had no money to do this. This was during the pandemic. We thought, oh my God, grad student needs a new project. So Sarah Azashar, I think you've been there, some of you have been there, it's like, time to pivot, gotta pivot fast. Okay, So we bought 8 new mattresses, so they were low price mattresses from 50 to $100. Oh, sorry, let me just have a second. In case you think, oh, Canada. Well, unfortunately, it's a pretty similar market. For those of you opposing tariffs, it's the same market. Okay. That wasn't directed to you, as you know, it was like, yeah, okay, so we could not, we were actually like 8 mattresses, and then 2 years later, we purchased another 8 to see if the results were reasonable. So we were really surprised. Here we have our mattresses and some SVOC concentrations on the y-axis, going to 45,000 milligrams per liter, so 45,000 ppm. And if I'm doing this right, if that the top one is 4.5% of the polymer. Okay, so this is the foam, and in the foam we found just a bucket load, because I'm using polite terminology, a lot. You know what other word I was going to use? A lot of the organophosphate esters. And for example, we found TSEP, which is prohibited from use in Canada. And sorry, these are paired, along here. I just want to point out the kids' mattresses do not need flame retardants. We looked into this in detail with some fire scientists. Although it's a small open flame flammability test, it can be met without the use of flame retardants. There's no reason to have flame retardants in the foam. By the way, the flammability standard is actually higher than for adult mattresses, which is a smolder test. So we were surprised to find TCPP, which is and TDCPP, and I know Chiha, you have done work on TDCPP. We were dismayed to find these 2 chemicals. These in 2014 they were recommended for regulation in Canada, and we've not moved on it. Moving along. We also, so this is in the cover. Now we're talking about the cover, and it's going up to 35,000 parts per million. And so the top value is 3.5%. And again, we found a lot of compounds. We found this mattress exceeds the regulatory limit in Canada. These 2 mattresses come very close to exceeding the regulatory limit. And then we have regulations for these phthalates, but only in products that are actually mouthed by kids, not for mattresses. But I would submit that the exposure that kids are getting from their mattresses directly is going to be comparable to something you would actually put in your mouth. So these are not regulated. And the last one, and similarly, this was coming close to a regulatory limit if mattresses, if you would use the 0.1% regulatory limit. So we were really quite surprised with these results. And then we went into kids' bedrooms. We did a mail out because we didn't go into anybody's houses at the time, and we used silicone rubber passive samplers. So they were put on top of the mattress, closed off to bedroom air, on top of the mattress, open to bedroom air, and then hung out in the room. And what we found for a number of the chemicals is quite a sharp gradient. This is the maps in the sampler, so that they're all comparable. And what you're actually, this is the fugacity gradient, because it's going from high in the mattress to open to mattress air to bedroom air, except for 2, DEP and benzophenone, that were higher in bedroom air.
Yeah, he's brand new.
No, these were, do you really want to know? They're like friends' kids,
Yeah, that's
right?
fine.
Because it's so hard.
But that's helpful.
No, it's okay. No, so the other one was brand new mattresses. This is just the kid. Yeah. And by the way, did you know that children sleep up to 18 hours a day? Like, wouldn't you like to do at least half of that? It's that the opportunity for exposure is so great. So we really ought to be paying attention to this. Okay, fugacity driven release, and again, to me, this emphasizes the inevitability of exposure. So, inability to sufficiently reduce exposures to protect populations, right? Because that is what we thought, at least previous governments did. We know what we're not, no. That was our supposition. So there are 4 arguments here that I'm going to go through in turn. Okay, so the first one is that we have unfettered growth of chemical production. We don't actually have chemical production volumes for individual chemicals because that's protected information. So we don't know, but for this is from the Global Chemicals Outlook 2 report that was published several years ago. And what we did is we normalized the production data, starting in the year 2000 going to 2016. And what you can see is this dramatic increase in total chemical industry, plastics for sure, petroleum-based chemicals, which is an awful lot of chemicals, and pesticide active ingredients right here. Chemical production has increased 50 times from the year 1950 to the year 2020, and is poised to increase a further 3 times up until the year 2050. We have no controls over total chemical production, which far exceeds the rate of population growth. So next, there's the uncontrolled proliferation of chemicals. So this is work done by my colleague Shen-Yun Wang, who looked at the chemical lists from from as many countries as possible, including China, Europe, US, and so on. They documented 350,000 substances that are registered for use globally. So these are all different compounds. 70,000 were registered just between 2010 and 2020. 70,000. So as you're looking at these numbers, think of regulatory capacity. And think of the capacity of our community to be investigated. So that's what you should have in your mind. 30,000 were registered in emerging economies, and we know that emerging economies are playing a very important role in new chemical production. The challenge there is it's not the lack of regulation, because many emerging economies have regulations. It's the lack of compliance monitoring and the culture of compliance. That's what the issue is. 50,000 are confidential, so you don't even know what they are, and 70,000 have ambiguous structures. So again, we don't know what they are. And this is exemplified by the graph. This was put together by Schumer at, no, it's not at all, 1997. So this is going from the year 1800 to the year 2000, and it is a log scale. So the highest number is 100 million. So it's an absolute exponential increase. This is the number of new substances that have been discovered. So the irony is that we're losing biodiversity, as you know, at an alarming rate. And we're increasing the diversity of chemicals at an also alarming rate, where we cannot keep up with figuring out what they are, let alone understanding their impact. So here's an example from plastics, and the reason why we're interested in plastics right now is because the world is in the midst of negotiating a plastics treaty. So that's why there's so much effort being devoted to plastics right now. So my colleagues, this is Martin Wagner et al., just published last year, 2024. About 16,000 chemicals are used in plastics. I've got the less than, I think it should be greater than. 100,000 different plastic formulations. with 6,300 having significant exposure potential. So that means, again, going back to the fugacity argument, when it's not chemically bonded, it migrates out, and most plastic additives are not chemically bonded. The minority are chemically bonded. So it's inevitable that they migrate out. 4,000 are known to be hazardous, and then Roland Geyer now calculated that there's an equivalent of 400 million tons of additives that are produced. So for many of us that have looked at chemical, like plastic additives like phthalates, we now see that the plastics in the form of microplastics and more so nanoplastics are probably the Trojan horse that delivers many of those additives into us as we're able to inhale them. And because the particles have a longer residence time than the chemical itself, if it's just pure gas-based inhalation. The inability to assess. So there are two studies that I'm aware of on this. I'll share the results of one of the studies. This is in terms of understanding ecotoxicity. It's the sheer inability to assess. So what Christensen et al. Did, it's a bibliometric study. They looked at 130,000 different papers. And of those, there were 33,500 different chemicals in all these papers. But let me see if I always have a hard time reading this graph. So the graph is the number of chemicals at the bottom going from 0 to 100. And then here we have publication frequency and also the cumulative frequency. So if we go up to 50%, 50% of the papers, and read over, dealt with 65 compounds. So 50% of the paper only had 65 compounds, but you see that it's much more extreme than that, because you see that you see this log normal, this log curve, where you've got a tremendous amount known about cadmium, mercury, arsenic, and pesticides, and so little known about the majority of the chemicals. So Derek Muir and colleagues did a similar bibliometric analysis with citations, and they also found that the majority of something like they looked at, they did a download dump, and I don't know, it's 1 million records or something, and similarly, very few chemicals are being worked on. And I'm one of those people, because once you develop a method, an analytical method, you stick with it, right? Because you're in the publish or perish mode. Like, who has time to go and develop a new method for something? It's in terms of your career, it's a risky strategy. And yet in terms of our lives, it's a risky strategy. So again, we know a lot about very few chemicals. This is just for plastics. So this is the number of chemicals that are used in terms of the mixtures of the total number of chemicals, 12,000 organic chemicals, mixtures of polymers, organophosphates, halogenated chemicals used in plastics. And we see that over 16,000 chemicals in plastics have CAS numbers. Over 25% of the chemicals used in plastics, they don't have a SMILES or INCHI code. You don't know the chemical formulation. You don't know the chemical formulation of over 25% of these plastic additives. Over 9,000, there's no publicly available information on the origin or uses. 10,000 of these chemicals have no product information. Like, it's just crazy. Here's another example of too many chemicals to access. So here's a case study. I am not even going to try to say the name of this chemical. But John Washington went out and sampled soils, and colleagues went out and sampled soils around New Jersey for this chemical that's used as a replacement for, get it right, Miriam, it's either PFOS or PFOA. You see, I lose these details. You'll believe me that, which one is it? Do you know? No, you were scratching your head. Sorry. Okay, anyways, so what they found is it was widely distributed in soil. So a chemical has to reach a high enough production volume and usage profile in order for it to be emitted, to be actually detected in soil. So this is not like a small amount of chemical. It's gone into high volume production. Yet the US EPA apparently had no data on it. The European Chemicals Agency knew that it was not acutely toxic, and the European Food Safety Agency knew that it was not mutagenic. So high production volume, and there's a great paper by Gold and Wagner. Where are the data? We will get through this and we will come out the other end. So, the inability to control exposure through risk-based chemicals management, and I'm sure you all know that the US in particular is highly wedded to a risk-based management system or assessment and evaluation system. These data from the Canadian Health Measures Survey is, and these are data for, this is expressed in micrograms per liter. For the blue bar is PFOS, the light blue bar is PFOA, and the red bar is PFHXS, which you cannot say quickly, I found. For age categories 3 to 5 years all the way to 60 to 79 years. And you can see from these data, well, I'm going to tell you, 98.5% of Canadians have measurable blood levels of PFOS, PFOA, and PFHXF at low microgram per liter levels. Do you know what the US EPA drinking water standard is? 4 nanograms per liter. 4 nanograms per liter. These levels are considerably higher than the drinking water standard. So why do I say it's a failure to protect populations? Because PFOS, this one, was first restricted in Canada in 2008. So these are data from 2016 to 2017. I mean, you probably are not surprised to see these data because you know, first of all, there's a long lifespan of that chemical in the products in the home. So it's like because new uses were restricted doesn't mean it goes away. It just means you can't scotch guard your couch again with PFOS. That's number one. Number two, it's got a long lifetime in the body. But it does speak to the problem of risk-based legislation. And I'll get to that. So the last reason is lock-in. So lock-in is, why does society continue to do harmful practices when we know it's harmful? What more evidence do we need? And the answer is, we don't need more evidence because we're locked into that use or that practice. We don't need more evidence of fossil fuels creating climate change. What we have to deal with is the lock-in problem of the use of fossil fuels. So that too is similar with chemical use and our exposure. So lock-in is the combination of economic factors, that we have an infrastructure that uses the chemical. We have social behaviors and attitudes that continue with the practice. We have technological lock-in, where we have the facility set up and we keep producing because we don't want to have those stranded assets. and political lock-in also, because even with our political frameworks, they respond so slowly to change. And they don't have the nimbleness to move forward and unlock us. So let's just look at an example of lock-in. This is PFOS. So between 1977 and the 1990s, 3M found evidence of its toxicity, that it was bioaccumulative, but continued to produce PFOS, as you probably know. So part of me also just has that emotional response of you knew it was harmful and you kept producing it. And not only that, you intentionally suppressed that information. And we know that and also try to sow seeds of doubt and uncertainty as to its hazard. And we have more information on how certain industries have enabled themselves to continue production by sowing the seeds of doubt and uncertainty. Anyways, moving forward, seeing a writing on the wall, 3M reached a voluntary agreement with the US EPA to stop producing PFOS between 1999 and 2002. And then, several years later, PFOS was listed under the Stockholm Convention with certain exemptions. Now, I should mention one of the widespread uses of PFOS, as I was said this morning, it was used as a defoaming agent in chromium plating, and it was seen as a risk management measure to reduce exposure to chromium-6, which is highly hazardous. So the use of PFOS was seen as a risk management measure. So the US is not a party to the Stockholm Convention, but there are 184 parties that are parties to the Stockholm Convention, including China, that have worked to implement national restrictions on PFOS. So that's how the convention works. So, but because the demand, so that's dealing with the supply side here. So the US shut off the tap, the demand continued. So between 2002 and 2006, Chinese production ramped up to fill the continuing demand for PFOS, because unfortunately, this voluntary measure and the US EPA did not work on alternatives assessment and implementation of alternatives that would have tried to stop this increase. So now to bring it around to full circle, and the irony here, so I find this very ironic. From 2011 until the present, from 2017 to 2023, the Global Environment Facility, the US is one of the big donor countries so far. And it's donated money through the JEF to try to reduce production in China. Is your head hurting? And I got the couch out there because PFOS was used in Scotchgard. So the key regulatory failure here was to restrict supply, as 3M did, without restricting demand and working on demand. So in other words, you have to do supply and demand side management. I mean, obviously it makes a lot of sense, but we don't do that. Okay, so now we're going to move into what we can do. So there's a whole laundry list, so I better get going on it. So the first one is why we need hazard and not risk assessment, which is almost like, it's almost heretical to say that. Here's the reason why. It's because to get a designation of risk, the exposure has to be high enough to have a hazard quotient, or for the risk to be of concern. By the time the exposure is high enough, the industry and society has locked into the use of that chemical. And you cannot just turn off the tap, as we just talked about with PFAS. That's why risk assessment doesn't work from a regulatory viewpoint. You've already invested so much by the time you have so much exposure as to trigger a risk designation. So what you need is, and that's because of lock-in, what you need is a hazard-based approach. The EU, the European Union REACH, has works somewhat on hazard with a hazard classification. So a chemical cannot be registered, cannot easily be registered, depends on the use, if it's carcinogenic, mutagenic, or has reproductive toxicity. We need to move to hazard-based regulation. Then there's chemical simplification. So as we talked about with all the plastic additives and so on, well, the plastic additives are not just problematic in terms of understanding what the implications are, but you can't recycle because of all the additives and you don't know what's in the additives. So it's an absolute impediment. So what's happened, at least with PET bottles, where the recycling rate has reached up to 39% recently, at least there is amongst the PET producers an agreement on the formulation of PET so that it can be recycled and so that you understand the sorry, I have to get back to it. Never mind the understanding. Okay. Now, there are the plastic treaty, I mentioned earlier that there are the plastic treaty negotiations. And so far, the US has been amongst the like-minded countries that have been, not high ambition, so not like-minded. So, has everybody been following the plastic treaty negotiations? Good, because that's depressing, so you don't want to go there. So, it's just like the same geopolitical crap that's going on. So there are the high ambition countries, which the US has been part of, and Canada and the EU, working towards reducing plastic production as the fundamental solution. And then there are the like-minded countries who produce oil, so the Gulf states. Guess who they're teamed up with? No, not yet. So the Gulf states, Iran, Russia, that are working to get out of the plastics treaty any restriction on plastic production, which is, and just turn it into, we need more waste management. So I'm going to talk about this, a cap on chemical production. It's purely, it's ambition, but I believe it needs to be said. I mean, I don't know how this could ever be implemented. But just as, the world, we have more carbon dioxide going into the world, we have activity-based restrictions, which are like emissions per unit of energy produced or, per mile driven. But the world doesn't care, right? Because activity goes up, you need hard caps, you need a total cap. So we need to have some type of total cap ultimately on chemical production. I'll keep saying it. Don't know how it could be implemented. Something that could be implemented is the essential use concept, and that is to phase out the most harmful substances from, in essence, the low-hanging fruit. So you don't go after stuff that's very, that's providing an essential use, but you go after the low-hanging fruit. And we were just talking about PFAS. You don't need PFAS in the dental floss. You don't need it in kids' uniforms. You don't need it in cosmetics. You just go after those non-essential uses. And when people say, but we can't eliminate it because we've got these essential uses, you say, no, we can, because you can select which applications are restricted. And that's how the Montreal Protocol has moved forward, which is for ozone depleting substances, probably the most effective multilateral environmental agreement. Breaking lock-in, so that's both the management of supply and demand, as we talked about earlier. So we need to broaden the scope of restrictions, engage all stakeholders, and have long-term proactive thinking. Imagine that, long-term thinking, oh my goodness. Okay, I'm gonna make a pitch for multilateral environmental agreements such as the Stockholm Convention. And then hopefully with the plastics treaty negotiations, and I'll tell you why. So I know that multilateral discussions are breaking down. In other words, multilateral means that a whole bunch of governments get together. But I'll tell you why I think they're so important. That's because those fora give a voice to lots of low-income countries who would not otherwise have a voice. And you see it at the negotiations. Very poignantly, they may not, we're all trying to do the right thing, but we have to have a forum where all the voices are heard. And it's not just, I'm bigger and I'm getting my way. And then the last I'm going to end on is precaution and sufficiency. So we've probably seen the donut economics of Kate Raworth, who talks about getting to the sweet spot. And this actually this goes back to these Earth system boundaries. So we know we have overconsumption that are pushing us outside the boundary, and yet we have poverty where not enough people have minimum needs met. So we have to find that middle ground where we reduce overconsumption and we bring up those that are impoverished. Now, the good news, this is the most recent paper I found from 2024, Tien et al. That the global 10% of consumers from all countries. So the difference with this analysis is that they disaggregated all the countries in terms of consumer power. The top 10% of consumers were responsible for the majority of reaching 6 environmental boundaries, of which climate is the primary one that's being breached. Now, I'm not naive. So this is like the third rail politically. You touch it and you die. But at least we can talk about it. We can talk about the need for sufficiency, and hopefully we can take that moral high ground. Or we can exemplify that in our lives. We do by example. So I'm going to end by saying, this is kind of what we bought into. We work at the university, we just feed our information into the bureaucracy, goes into government, creates positive change, and then we have this we have this cartoon that says the climate scientists in uproarious laughter, the COVID-19 scientists say, as long as we just provide the facts to the American people. Well, I want to end on a positive note. And that positive note is taken from the work of Thomas Homer Dixon, who I think is just one of the most cogent authors right now. Regardless of your political orientation, almost all of us hope to have a life of opportunity, a life of security, justice. And then what he talks about is a shared identity of we. It's not identity politics, but it's rather the sharing that we're all in this together. Even the driver who took me here this morning, who said, when he asked me about tariffs, and I said, Dad, I said, it's all a bunch of lies. And he said, we all have different interpretations. I restrained myself and knew that he was human, and he too wanted these primary goals. So I'm going to end with something that I find inspiring, which is a quote from Thomas Homer Dixon, that we all have a commanding hope that's honest about the dangers ahead and astute about the strategies we should use to face those dangers, and one that powerfully motivates us. Let's not aim for what's merely feasible and falsely hope that it will be enough. With commanding hope, let's aim for what we all consider enough, a future in which our children and life on this planet can flourish. With that, I'd be pleased to take your questions. Yes, please.
So it feels like this is all like a failure for everybody that's involved, right? Like we all play a part in here. But what can we in academia do when we present things and, you know, it's met with just like, fire on, no, now moving on. So like, how do you like approach those issues and try to move forward with your like
Yeah.
things, right?
Can I just say, I don't think it's a failure of all of us. I think it's a failure. It's not our failure, but it's rather that there have been very successful marketing of the alternative narrative. So I'd rather not see it as our failure so much as that we have not been as successful at grabbing the narrative. So how do I move forward? I do research that I hope is impactful. I work to get it out into the media, like I'm going to work hard to get our mattress work out. Now, it's a very small step, but when we embarked on the work, I thought, well, at least it'll put pressure on the mattress manufacturers. So I try to do impactful work and I try to speak my truth at these other fora like the Science Policy Panel and so on. So I just continue to work to speak my truth. And that's why I'm so glad to be here today, so that we can join in this conversation and that we can support each other to speak our truth. I don't know who's first, but I'm gonna.
Just, well, following up on that, you mentioned with the total chemical production, there was some information that's confidential, like on specific chemicals. What was the original justification to make that information confidential, and like, why not make it public aside from the benefits to the chemical manufacturers, and also as academics pushing truth, how do you push your message in with that uncertainty and information being withheld from you?
That's a very challenging question. Confidential business information is it's embedded in regulatory schemes, so that Coca-Cola can protect its formulation, even though now we can sort of back analyze and find out what's in Coca-Cola. I think we have to keep pushing for disclosure. It's working more successfully in some jurisdictions like the EU. And it seems like an impenetrable and very difficult argument to make in North America, where there's a much different relationship between industry and society. So we keep pressing for disclosure, and it's extremely challenging. We have to keep pressing for it. At least California Prop 65, at least there's an example of public pressure for disclosure. I mean, of course, that's only a small number of chemicals, but it's the idea of the public right to know. Yeah.
Is it like the last picture we were talking about is disclosure of?
Oh, it is. Yes, I think the chemical manufacturers are very certain to ensure that confidential business information remains in the books. Absolutely. Yeah. Yeah, and so that's just the identity of the chemicals, let alone the production volumes. Yeah. Kristen?
I have a question on the mattress study. Is there any relationship with price? In the
No, I didn't show you that, but there was, so, sorry, I cut you off. There was no relationship between price and between additives at all. And we've looked at that for other things as well. But let me just add one other point to that, because I showed all those additives to the cover, including all those phthalates. You know what's really interesting? Only one of the covers with PVC, right, which I mentioned is rigid, and all the other covers were made of these new polymers that are inherently flexible. Sorry, inherently flexible polymers on the covers, and you've added plasticizers. That's a good lock-in. Are there any other questions or questions online? Yes, please.
So you were talking about like the mills high demand that which promote to low out
Yes.
production, and then the something to potentially address is by like distinguishing the essential demand and not, and also provide alternative for the other one. So given that some of the things are already in like clothes and in clothes, whatever, and how do we think of like, oh, if it's already there, it's because there's a demand, and if people prefer to use it, it's potentially a necessity, and who gets to decide if this is, based on what factors these are in this kind of society is essential or not. And that's part of the question. And also, when we were in journal club and we read the new like studies of things, it felt like the alternatives potentially are just potentially equally toxic. We just haven't accumulated enough data to prove that yet. So how do we know if the alternative, like how do we introduce alternatives? Except returning all the way to cotton stage. But
Okay, so your first one is about demand, and that's really great. I happen to be a technological determinist, and that means that I believe that as opposed to technology is neutral, that technology changes behavior, and that certainly industry has put substantial effort into generating demand. For some reason, society managed to function without deodorant for a very long time. And now it is seen as absolutely essential.
yes,
So we,
long work done.
well, I'm not gonna go into that one in more detail. I think that many parents do not realize that they're scotch guarding their kids when they put their kids in a PFAS containing uniform. So that to me, that's a creative demand. Somehow school uniforms and kids' clothes manage to not have stain repellent in them. That's very much an induced demand. And I think the advertising industry has grown up to understand and perfect induced demand. So that's that part. And I think that we can do thoughtful analyses to distinguish between a truly essential use. I'm going to have a fluoropolymer in an implant because it's inert and because it provides a very important function, and there are not alternatives. However, it's coating the outside glass of a fancy building with a fluoropolymer is a non-essential use. So I think we could do that. Sorry, the second question?
Alternatives.
Oh, yes. So I'm actually going to, I hear what you're saying, but I think many alternatives do have lower harm. Number one, we understand more about persistence. So that I'm not saying we're 100% on this, as we were talking about all the pharmaceuticals that are now qualified as PFAS. But we have a better understanding of persistence. And we do have a better understanding of at least what's acutely toxic. We have advanced, we have improved our understanding and our screening tools. I do believe we have advanced.
The last question.
Yeah. Please.
Thank you for such a fantastic talk, as always. So seeing that exponential growth, right? Have you read or can you foresee if we stop now, though, even if we stop now, this is still go on. So what is the best case scenario here?
So I think, sorry, you broke up a bit. So I think correct me if I get your answer. We have so many chemicals that we use every day in our lives, in our technology. So even if we stopped using, for example, PFAS in non-essential uses right now, it's going to continue. And that's absolutely true. And we did do that type of modeling, for example, with polybrominated diphenyls, which speaks to why you do have to act in a precautionary fashion. But we have to have hope and we have to do what we can do. So we have to say, right now is the time to stop non-essential use of chemicals that we know are toxic and hazardous. Like, how surprised were you to see that in 2024, we're getting mattresses containing chemicals that shouldn't be there? So there are things that we can be doing. And I just have to hold on to that.
It's great.
Thank you.
Thank you.